Thank you. So I'm Michael, and this is Chris. I work on LLVM-libc, and
I work on libc++ and occasionally Clang.
yeah, and so we're here to talk about a project for sharing some code between LLVM-libc and libc++. So let's start at the beginning. Like, why do we need a libc in LLVM in the first place? Like, you could say it's to complete the tool chain, and so we can make it more standalone and self-hosted, but like, LLVM is not written in C, it's written in C++. Why do we need a libc? And the answer is basically, libc has become the foundational library for a lot of languages. So like, Lua and Python are interpreted, and their interpreters are written in C, and they call out to libc for a lot of functionality. Mojo and Rust are both compiled languages, but their standard libraries also call out to libc because, who wants to write the math functions or like string to float conversion? Those are hard. And then C++ is perhaps the most extreme example because libc++ actually contains all of libc inside of it, or the standard says it does. Obviously, they're separate libraries. And so, libc++ does this provides a nicer interface for a lot of libc functions. So here we can see like the sign function, they make sure it's defined in the global namespace if you want to call sign f directly, but if you want to just call sign on your float, then there's a function overload, so you don't have to specify all of that. And then if you're including cmath, then it'll also include math.h, which is the libc version, which includes all of the like libc parts for it. And so like a lot of libc functions, there's the libc++ interface, and then some specifics, and then they like call into a libc function for the core functionality. And so for this like nicer interface in C++, LLVM-libc is implemented in C++. So we can do things like template our internal functions for like string to integer, because you have like a to I, and str to l, and str to ll, and str to ul, and str to ull. And these are all like different functions that perform slightly different things, but like the code could be identical if you had templates. If you're writing this in pure C, then you're gonna have to do things with like macros and duplicating code so that you can get a decent interface. So C++ gives us a better syntax abstraction and a cleaner function interface internally, even though externally we're still providing that same C function interface. And we designed it to be modular, at least in part because these internal functions, they need to be completely internal. Like we can't expose them. So like our own interface, we want our own interface internally to be more C++-like because it's more convenient. So let's talk about libc++.
So yeah, libc++ has a much larger surface area than libc, just generally speaking. And libc++ has had a few missing features from C++17 for a while. And some of that is because floating point numbers are particularly hard. Whole textbooks have been written on understanding how floating point numbers work, and that makes them scary. And we want to make sure that we get these sorts of things right, which means you need to put in a lot of care. And so we haven't actually gone and implemented this for quite a while. So C++17 specifically added something called from chars, which is in the char-conv header, and it's about converting strings to floating point numbers. And there's also an integer overload, not really relevant for now. Now, the most important part of what's on screen, which is called standardese, it's the text that the C++ standard has, is the bit that's in bold that says that from chars is almost identical to C's str to d. It has a few exceptions, but otherwise its functionality is supposed to be the same as the C library function. But if we contrast the two interfaces, we can see that they're quite different. The C++ one takes a range of characters that is delimited by 2 pointers, whereas the C function, str to d, takes a null terminated string. And the way in which they hand back their values is different. In C++, it's returned as a reference to a floating point number, whereas for strtd, it's returned as its return value. And the return value from chars contains different information. There's also a format specifier, and the way in which they return their errors is different. In C++, it's a part of that from chars result, whereas strtd returns it via errno. So the error channels are different, and so the interface is just completely different, but the functionality is the same. And so really that leaves us asking, well, why can't C++ just roll its own thing? And again, floating point numbers are ridiculously difficult to get right. And so why should we spend time rewriting 2,300 plus lines of code for something that libc has already done? It would be really nice if libc just had a different interface. And the good news is that LLVM-libc already does this. So LLVM-libc uses a function template for its string to float conversion, so that way they don't have to stamp things out for the strtf, strtd, and is it strtld? Strtld. And so that's great because they're function templates that have to be implemented in headers, which is great. And because it's just string to float conversions, there are no OS specific dependencies. And so that makes it really easy for us to maybe work together. So the real question then becomes, well, can libc++ use the code that LLVM-libc has already provided it, so that way we can implement from chars with a common core? And if we wanted to go down this path, then we'd need to consider what libc++ would need to do and what libc would need to do kind of separately. So from the libc++ side, things need to be user transparent. That more or less means that we need to have a strict interface that limits Hiram's law. Now, Hiram's law, for those in the audience who don't know, is an observation that was made by Hiram Wright about if there is something that is user touchable. It doesn't matter whether or not you document it. Doesn't matter whether you say, "Do not ever interact with this; it will break." Users will eventually come to depend on it as the user base grows, and that is something that we need to contend with. And so it needs to be provided in such a way that users don't even know that it's different. It's following the as-if rule that C++ provides, where if you can do something slightly differently, but it behaves exactly the same, then that is good enough. But it is an unstable API. And so that means that we need to have a very explicit narrow interface, so that way we can avoid limiting the evolution of this particular library. And we also need to have a plan for API changes, because things do change over time, and we need to make sure that we are not limiting ourselves by not having a plan. That is very important. And finally, Michael, I mentioned at the start that I occasionally work on Clang. What would happen if I, say, wanted to start pulling things in on the Clang side?
I think that's a great idea and something we should explore in the future, but we need to be careful and explicit about this. If you start like randomly including libc internals, I'm gonna scream. Please don't. Oh, yes, that's right. So from the LLVM-libc side, what do we need for this to be success? So like the code is already written in standalone C++. So like we have an API similar to what libc++ wants. We needed to make a couple of tweaks, but nothing major. And I already gave a talk in 2022 on this being a well-optimized implementation. And for making that like explicit narrow interface, the header-only implementation means we can do indirection headers where we redefine the parts we want to expose in a specific namespace so that it's explicit, like these are the parts you can touch and these are the parts that are even more of an implementation detail just for libc. So this is an example of one of those headers, and so we're providing str to integer, but we're not providing like the thing that converts a char, like a char in base 16 to an integer. So like, what about the potential problems? What are the pitfalls that we want to avoid here? So the first one is coupling the public API can severely limit evolution. So when I first proposed this, one of the glibc maintainers brought up an example of a time that glibc and libstd C++ tried this and it went badly. So they did what they called libio vtables, where you could use a C++ stream as a C file star, which, if you think about it for a second, it's a cool idea. They describe it as the cool way, and it's an interesting way to do it, but it does not have that many benefits in the long term, and it severely limits how you can change these APIs, because now you need to make sure that your file star and your stream are in sync. So the eventual solution that they ran into was that they could not update this without breaking the API, so they broke the API because that was the only option they had. And then what if they diverge?
Well, if they diverge, all we really need to do, because this is evolution, really is just move back the common ancestor. It's so what we do is we start with the existing API, and then we work out what the common functionality between the two new APIs are, what the divergence is, move the divergence into the respective libraries themselves, keep the common interface common to both places, and that's it. There's not really much of a change other than just a bit of shuffling to make sure that we meet the specifications of the respective libraries. And if they completely diverge, then all we need to do is take that one function and split it out entirely. So that way everything else remains the same, but the thing that has diverged is now no longer a part of the common code. This makes it a little bit difficult unless we adhere to the previous expectation that we are going to have a very strict and narrow interface that we follow, and always need to make sure that we are following, so that way we can robustly adhere to this part of the plan. And Michael, it's possible to do this because libc and libc++ are part of the same monorepo. Is that right?
Yeah. So if we were two completely separate libraries and we wanted to do this sort of internal sharing, we'd need to worry about API versioning and what versions of libc support which versions of libc++. But we're in the same monorepo, so if we want to change the API, we can change it in one atomic commit, and then as long as everyone is building their libc and their libc++ from the same commit, it shouldn't have any issues. There's no API versioning here because the API version is a single commit. And based on this, it seems like it's going to work. So I think there's only one thing left to do. So we did it. So LLVM 20 will ship with from char's floating point. And it's going to be based on the LLVM-libc code. You can see the pull request up on screen, but it has merged, and it hasn't broken anything too bad. We had a couple issues with PowerPC, but nothing too bad. And from everything I've heard, it's been a success for both libc++ and LLVM-libc. And now we have a shared common core that we can work on together.
I agree. Thank you.
Yeah. A couple of special thanks for people who helped out with this project. Louis Dion, head maintainer of libc++. He helped out with organizing the libc++ side and also with a lot of code review, because I can't review the libc++ code. And speaking of not being able to review the C++ code, I also can't write it. Mark the Weaver wrote the libc++ parts, so all of the string parsing. So big thanks to them. And then also everyone who participated on the RFC and on the pull request. There were a bunch of other people, but I want you to know I appreciate all of that as well. And then there's some places we're considering future work.
So for the future, there are other areas that we suspect libc++ might benefit, and so that would be great. It may also be nice to put this sort of thing in other parts of LLVM. For example, at the keynote this morning, Aaron mentioned the context for math stuff. That could be a potential avenue for sharing with other areas of LLVM. But again, don't just start willy-nilly including this in other areas of LLVM. Please talk with the hand-in-hand folks, because Otherwise, Michael will get very upset. And finally, it might be nice to one day entertain the idea of building a single unified library that contains all of LLVM, libc, libc++, libunwind. So that way you only have to link one thing as opposed to having to remember which parts of the LLVM runtimes that you want to combine into building your program. And with that, Michael, did I leave anything?
I think that's it.
Okay, with that, this is Project Hand in Hand. Thank you so much. We'll be happy to take any questions now.
Thank you so much, Michael and Christopher. So there are two mics. Either feel free to line up behind that one, or I can pass the mic to anyone else if you have questions.
So part of the problem here seems to be a sort of divergence between C and C++. Is there any hope that maybe like the C++ functionality doesn't seem like it would be not useful for C? Maybe we should like define a C20Y version that has that new functionality? Because if we had a public, like if we had a public standardized C function that did the thing that C++ needs, we could just call it directly and not have to do all of this work.
That is true. If the C standard community wants to add from char's floating point in some like slightly different interface, you can't do it the same way, then we definitely could look into that. You'd still have issues around errors and things, because the libc function returns an error by setting errno, and I believe libc++ doesn't. And there's also like rules around when you're allowed to reset errno. So I like the idea. I'm not sure we could do it perfectly, but I think you could definitely get a lot closer.
I mean, if it was just that, you could wrap it with a function that saves and restores errno. Like, you know, like if that was the only issue. But I think, I don't know, the bigger issues were like, from that two-sentence summary, it was like, it uses different parsing rules. It doesn't use locale. And like, not using locale, I'm sure is a thing that every C programmer wants, right? So, I don't know, it seems like there's some scope here for doing something in C. I don't know.
Yeah, I think we definitely could look into doing that. Perhaps another area of future work.
Hello, what does testing look like?
You're right.
So from the libc++ side, the testing looks just like any other unit test. We're just testing the public functionality. On the libc side, we have our own unit tests exercising the internal code and also like our public interface. So we know that the parsing, but also like the conversion works on our side. But from the libc++ side, we're not testing any of the like hand-in-hand specifics. We're just testing this as if it were any other libc++ function.
Right. One thing to remember is that it is user transparent. And so there's just a bunch of unit tests from the libc++ side to ensure that it is still from chars and everything else is kind of behind the scenes.
You mentioned that LLVM-libc, or sorry, not LLVM-libc, libc++ requires some changes to be able to get this work. Were there any significant changes for LLVM-libc side on the internals that were required? And did you find any of them limiting in like how you would implement LLVM-libc? And that could potentially restrict future directions that LLVM-libc could take?
So we did need one minor change on the LLVM-libc side. There was like there's a specific pass of string to float where you need to reparse the string for like performance reasons, and so we had to add a length limiter to that. But other than that, it didn't require anything major, and so far we haven't run into any places where it would be a major maintenance burden to like to add the functionality that libc++ needs. If we did, we'd probably want to sync the interface down so that it's not so that we're below the layer where that would be a problem.
Nice talk. How do we mix? It looks like libc++ has a dependency on LLVM-libc, right? So if a user wants to mix a different version of libc, say like muscle with libc++, which I think a lot of traditional users do, like won't this cause a compatibility issue?
So yeah, I had a similar question myself, and from what I understand, the idea is that it's built separately. So libc has its own component, libc++ has its own component, but it's still just the same code in that's being called. Did I miss anything there?
Yeah, well, that's accurate. And also, the dependency here is only internal. So like the public libc functions are still getting called through the public interface. This is just a special like internal interface for this one specific function.
But if you want to use muscle as a C library,
Yeah.
and libc plus LLVM,
Yeah.
it might be missing some functions, right?
No. Well, yes, kind of. Basically, you can think of the libc code that's being shared here as being effectively internal to libc++. So
Okay, I see.
It's not like muscle doesn't provide it, but muscle doesn't need to provide it. It's just like it's inside of libc++.
Are there, sorry to ask one more question, like, are there going to be multiple libraries? Like one, like we have libc++ as libc++, libc++ ABI, there's LLVM-libc, and then is there going to be another layer that has a commonality between libc and libc++?
That was one of the options we explored when doing this design, and it might happen, but I'd say not anytime soon. Basically, right now, all of the code is inside of libc, and pulling it out would be a pain because we have this like nice narrow interface to libc++, but inside of libc, we haven't been like trying to keep the interface narrow within our own library. So pulling it out would be a pain. We did consider it, but basically, right now the code is being maintained by the libc developers, and so
Okay.
having it as a separate library would mostly just be confusing.
It's just shared via headers right now. There's no runtime library that exists for any of this code share.
Yeah. Like Nick said, it's all shared by headers, so there's no like separate like runtime libraries that are being
I see.
linked.
Thank you.
Hi, I have a question. I'm Ravi from Apple, and great work. Sorry. I'm curious, what's the scale of, so Apple is one of the vendors of libc++ that you might know. So from that perspective, I'm wondering what's the scale of the change that we should expect here, and what cadence. I think every change involves some amount of qualification and testing. So it's interesting for me to know.
So if you're trying to build libc++, if you're doing it just in the CMake, you don't need to do anything at all. We like hooked it up already. If you are doing it in your own build system, if you're doing it like in GN or Bazel or something, there's a couple of things you'll need to hook up, but it's mostly just you need to point and include path. When building charconv, the like library for charconv in libc++, you need to include the libc directory, and you need to define one macro, and it should just work.
Yeah, cool. Sorry, I meant what is the scale of APIs that are expected to undergo this kind of change? And would that be like hundreds of APIs, or and what cadence? That's where I was coming from.
If I understand correctly, you're asking about what the scale, like what the impact will be on users. Is that future changes? So my understanding is that the future changes should basically behave in the same way. It's not really going to impact users, except they will get the functionality that they've been promised by the standard, and it will be delivered by adding more code, just like you would to when you're building out libc++ and adding new code directly to libc++.a.
Yeah.
Like hundreds of functions? Or?
For the number of functions, it depends on like exactly where it goes. So for like direct changes, I'd say maybe like 10s or 20s in libc++. But if we end up doing the const expr math through this, then that would be like 500 functions, but that's just because there are a lot of math functions.
Okay, yeah, if that's it with the questions, then let's thank the speakers again. And our next talk begins in 5 minutes.